Okay, let me begin a review of hypothesis testing, a review of the concepts. In hypothesis, there are two statements. One's called the null hypothesis, the other one is called the alternative hypothesis. The alternative hypothesis is usually the research hypothesis. It's the hypothesis that the researcher is trying to prove. The null hypothesis is the hypothesis that the research hypothesis is not true. You try to prove the alternative hypothesis, the research hypothesis, by disproving the null hypothesis. That's one reason they call it the null hypothesis. You try to nullify it. To set up a test that will make the decision to accept or reject the null hypothesis, you have to choose a statistic. It's called the test statistic. There's techniques for developing test statistics that are very useful. Then you divide up its range of possible values into two, the acceptance region and the critical region. Then to perform the test, you collect the data, compute the value of the test statistic, and then you make the decision. If the value of the test statistic is in the acceptance region, you decide to accept H-naught. If the value of the test statistic is in the critical region, you decide to reject H-naught. The two-tailed Z-test for proportions. Here we're testing the probability of success in a binomial experiment. The probability of success could be a proportion in a population, testing whether that value is some value. So you have this success-failure experiment. It's repeated n times. If you're sampling from a proportion, choosing an individual at random from the population is the success-failure experiment. The probability of success, P, is unknown, and we want to test whether it's equal to some specified value. We'll call that specified value P0. So P0 will be a number that we're trying to test whether P is equal to P0. The alternative is that P is not equal to P0. This is a two-sided alternative. It could be true if P was less than P0 or if P is greater than P0. The test statistic is the sample proportion P hat minus P0, the one you're testing, over the standard deviation of P hat when P0 is the correct proportion. That's square root P0, 1 minus P0 over P0. That will have a standard normal distribution, the way it's, if H0 is true. So the acceptance region is in the middle, minus Z sub alpha over 2 to plus Z sub alpha over 2. Z sub alpha over 2 is a table value from the standard normal distribution. It's a critical value. Z sub alpha over 2 has an area of alpha over 2 above. The critical region is outside of that acceptance region. It's greater than Z sub alpha over 2 or less than minus Z sub alpha over 2. The one-tailed Z-test for proportions. Again, you're testing the probability of success in a binomial experiment. The null hypothesis is that P is less than or equal to P0 against HA. P is greater. You'd choose this alternative if that was your research hypothesis. You're trying to prove that the true proportion is greater than the specified value. The test statistic is exactly the same that you use in a two-tailed test. The acceptance region, though, is only located in the upper tail. It's only those values that indicate HA should be accepted. You reject H0 if Z is greater than Z sub alpha. Reject H0 if Z is greater than Z sub alpha, accept it if it's less than or equal to Z sub alpha. You can compare statistical tests to a meter. The white part of the meter is the acceptance region. where the pointer points at, that's the value of the test statistic. If it's pointing in the acceptance region, you accept H naught. Critical region is the red zone. And you could have critical region located on both sides of the acceptance region. So that would be similar to a two-tailed test. When to use a one-tailed test or a two-tailed test? As I pointed out before, the alternative hypothesis is the research hypothesis. It's the hypothesis that the researcher is trying to prove. The researcher will prove with a margin of error the alternative hypothesis if he disproves the null hypothesis. If he nullifies the null hypothesis. If the alternative is two-sided, he'll probably use a two-tailed test. If it's one-sided, he'll use a one-tailed test. This is not always the case because there's some test statistics in which it's really the values of, it depends on the test statistic and which values of the test statistic indicate HA. So in a two-tailed test, if the test statistic is in the acceptance region, you accept H naught. If it's in the critical region, you reject H naught. So sometimes the critical region is located on one side of the possible values of the test statistic. These are called one-tailed tests. Whether you use a one-tailed test or a two-tailed test depends on the hypothesis being tested, and it depends on the test statistic. If only large positive values of the test statistic indicate HA, then the critical region should be in the positive. That'd be a one-tailed test. If only large negative values of a test statistic indicate HA, then the critical region should be located totally in the negative tail. Another one-tailed test. If both large positive and large negative values of the test statistic indicate HA, then the critical region should be half in the positive tail, half in the negative tail. It'd be a two-tailed test. So usually one-tailed tests are appropriate if HA is one-sided. Two-tailed tests are appropriate if it's two-sided. Not always though. Depends on the test statistic and which values of the test statistic indicate HA. Once the test statistic is determined, to set up the critical region, you have to find the sampling distribution of the test statistic when H naught is true. This describes how how test statistic will behave when H naught is true. Then you locate the critical region in the tails. Size of the critical region is chosen so that the area over it is equal to alpha. This ensures the probability of type 1 error. Rejection H naught when it's true is equal to alpha. Deciding that the research hypothesis is the correct one when H naught is true, when it's not true. To find the probability of a type 2 error, that's a more complicated calculation. You have to find the sampling distribution of the test statistic when H naught is false. The red region is the region where you accept H naught. That's the probability of a type 1 error. Type 2 error occurs when the test statistic is in the acceptance region and H naught is false. So that's that area there. That's a difficult calculation. When you're doing research, quite often the person who's granting you the money wants you to calculate probabilities of that your procedure will make a type 2 error. Type 2 error the probability of a type 2 error can be decreased if you take more data, if you use a more efficient sampling design. You want to be, if H naught is false, you want to be able to conclude that it's false. The p-value approach. This is an alternative way of hypothesis testing. You have a test statistic. Usually you have a critical and acceptance region. The critical region is set up so that the area over it is equal to alpha 0.05, 0.01. The value you choose, 0.05 or 0.01, depends on the seriousness of a technical error. There's this distribution of the test statistic when H naught is true. There's the critical region and the acceptance region. With this choice, chance of accepting H naught when it's true is equal to 1 minus alpha. The chance of rejecting H naught when it's true, that's a type 1 error, is equal to alpha. The test is carried out by computing the test statistic and then making a decision. The value of the test statistic may be in the acceptance region, but close to the critical region. It may be in the critical region, but close to the acceptance region. To measure this, you compute what's called the p-value. The p-value is the probability that the test statistic is as or more extreme than the observed value of the test statistic when H naught is true. More extreme means giving stronger evidence to rejecting H naught. So for example, suppose I'm using the Z test for the mean of a normal population. I'll use alpha equal to 0.05. Critical value is 1.96. This comes from a table. So the critical region would be to reject Z is greater than 1.96 or less than minus 1.96. Suppose you get 2.3. That's in the critical region, so you'd reject H naught. The p-value is the probability of getting a value at extreme. Probability of being greater than 2.3 or less than minus 2.3. Both of those are more extreme than the value of 2.3. Those can be looked up in a table. The p-value works out to be 0.0214. If the p-value is small, you should reject H naught. That's the probability of getting a value that extreme when H naught is true. If it's small, that should be rejected. So there's a graph. The gray area is the critical region for a Z test with alpha equal to 0.05. The observed value of the test statistic was 2.3. The black area is the p-value. If you got a value of 1.2, you would have accepted. The p-value is the probability of getting a value as or more extreme than 1.2. Greater than 1.2 or less than minus 1. You can look that up, and that's 0.2302. So there's a 23.02 chance of getting a value as extreme as 1.2. That's fairly high. There's a fairly high chance that that will happen. So you wouldn't reject the value there because the p-value is not small, it's reasonably large. There's a graph showing the p-value in that. If the p-value is small and you can use 0.05 or 0.01, H naught should be rejected. The p-value really is measuring the plausibility of H naught corresponding to the observed value test. If the test is a two-tailed test, p-value should also be two-tailed. If the test is a one-tailed, p-value should be 1. So this is a common way of reporting results. You report the p-value, then the reader can use his value of alpha to see whether H naught should be rejected. It also gives some indication of the strength of the decision to reject H0. If the p-value is extremely small, the strength of rejecting H0 is much larger. The next topic will be considered students' t-test. The reason it's called students' t-test, the researcher who developed W.W. Gossett worked for a company and didn't want his name known when he published the article, so he published under the name of student. This is the Z-test for means. Test statistic is the sample mean minus the hypothesized mean over the standard deviation of the sample. The standard deviation of the sample mean is sigma over square root. If you don't know the value of sigma, you can replace it by S. Now, student found that this doesn't change the distribution of Z to a normal distribution, except when n is small. When n is small, there's quite a bit more variability introduced into the statistic by replacing sigma by S. So the sampling distribution of this statistic is the standard normal distribution. Replacing sigma by S leaves the distribution unchanged, but only if the sample size is large. Student found that it has a little bit different distribution when n is small. For small sample sizes, the sampling distribution of that statistic is called student's t distribution. The degrees of freedom is n minus 1. 1 degree of freedom is used to estimate mu. That's x bar. The remaining degrees of freedom are used to estimate variability, estimate S. The properties of the student's t distribution, similar to the standard norm. It's symmetric, unimodal, centered at 0. It has a bit larger spread. That's because of the extra variability introduced by replacing sigma by S. It has a larger spread about it. It has heavier tails. As the sample size increases, the t distribution approaches the standard normal distribution. There are some graphs of the t distribution. The one which is more spread out, has the heavier tail, has a low number of degrees of freedom. As you increase the degrees of freedom, the t distribution approaches the standard norm. On here, we got degrees of freedom. The black distribution is the t distribution. The red is the standard norm. So when degrees of freedom is 30 or higher, the t distribution is exactly the same as the standard. So it's a situation when you use the t distribution. You have data coming from a normal population. Both the mean and the standard deviation are known and have to be estimated. The estimate of the mean is the sample. The estimate of the sigma is S, the sample standard deviation. We want to test if the mean is equal to mu naught. The test statistic is the same as the Z statistic, except sigma is replacing S. This statistic has a t distribution with n minus 1 degree. So you find these critical values. These are not underneath the standard normal distribution. They're underneath the t distribution with n minus 1 degrees. If you change the degrees of freedom, you get a t distribution. So there's the two-tail test. There's the one-tail test when the alternative is one-sided. So critical values for the t distribution. There are points underneath the t distribution that have an area above. Area could be alpha, or it could be alpha 2. You can find these critical values in a table for the t distribution. You can go onto the Stats 244 website to download that. There's what the t distribution looks like. Along the top, we get the area. Above, the values. Along the first column, we get the degrees of freedom. That will be the sample size minus 1. So to look up the t value for a specific value of alpha, you'd look for the value of alpha on the first row, and the value of the degrees of freedom along the first column, we get 2.4%. If you go to the very last element, infinite degrees of freedom, that's the standard normal values. So I'd given you a table for standard normal values before. Those values are just in the last row of the table for the t distribution. Example, suppose we're measuring weight loss on a new diet, and we take 6 cases. We want to test if the diet is effective. The diet
Is
is
that
effective
regional?
if the weight loss,
Because I'm not
average
seeing
weight
it
loss,
on my main
is
browser.
positive. It's not effective if 0 or less, even less than 0. So there's the hypothesis we want to test. There's the test statistic. The critical region would be a one-tailed critical region, which we're trying to prove a one-sided alternative. There's the data. Notice that this is weight loss of 6 subjects. The one where there was a negative weight loss meant that a person gained weight. The average is positive, it's 0.9667. The standard deviation of those 6 measurements is 1.46241. So the test statistic is x bar minus mu 0. Mu 0 is 0 over s divided by square root of 6, 1.619. The critical region is t greater than t.05 for 5 degrees of freedom, which is 2.015. So since t is not greater than 2.015, it's 1.619. Our conclusion is to accept H0. Again, that we haven't proved H0. We haven't been able to disprove it, prove J. Confidence intervals. There's the formula for confidence intervals for the mean when standard deviation of the population is x bar plus or minus z sub alpha 2 sigma over root. The probability that mu lies between those two values is equal to 1 minus alpha. If sample size is small and we replace sigma by s, we have to take into account the variability that you'd observed in s. The critical region, rather than z sub alpha over 2, we use t sub alpha 2. So this is that data before. This is measuring weight gain on a new diet. The average weight gain, sample weight gain is 0.9667, standard deviation 1.624. There's the formula for the confidence interval. Instead of Z sub alpha over 2, you have to use T sub alpha over 2 for 5 degrees of freedom. It's 2.571. The 1.6 is S. N is square is 6. X bar is 0.966. So that confidence interval is minus 0.57 to 2.50. So the average weight gain on this new diet is somewhere with 95% confidence, somewhere between minus 0.57 kilograms to 2.50. So just a quick summary. Estimation by confidence intervals. There's the formula for confidence interval for a proportion. Sigma p hat is square root p1 minus p over n. Replacing p by p hat is not a big deal because usually the sample sizes are quite large. When they're usually quite a bit greater than 30, they're up around 100, sometimes a couple thousand. The error bound b is what you add and subtract the p hat to get the upper and lower confidence interval. There's the formula that will give you an error bound of b, level of confidence 1 minus alpha. Now, it depends on the proportion that you're trying to estimate. So you might have to, in order to do this calculation, you might have to have preliminary estimate of p. And again, if you don't have a preliminary estimate of p star, use p star equal to 0.5. Confidence intervals for the mean of a normal population. Here I'm using the critical value from the standard normal distribution. This is okay when I place sigma by S. Sometimes sigma is known. In measurement instances, for instance, if I'm measuring speed of a car, the accuracy of the radar machine could be known. So sigma could be known in that case. If sigma is not known, you have to replace it by S. This is not a big problem if the sample size is large. There's the formula for the value of n that will give you an error bound of p, level of confidence 1 minus alpha. Again, if there's a lot of variability in the population, if sigma is large, you'll have to choose a larger sample size. There's the confidence interval, the mean of normal. It's the same as before, except we're replacing Z sub alpha over 2 by a value for a t from the t distribution. This is to take into account the variability introduced by placing sigma by S. Maybe we'll stop at this point and I'll end the lecture and ask if anybody has any questions. So today was a short lecture, just a half an hour. The next test is on February the 22nd. Again, I'll give it out beforehand. Practice exercises for test 3 are posted on eStats 245 web. So at this point, we'll end the lecture.